and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module we will begin to look at various modulation formats and how can we analyze the performance of those systems. We will begin with a very simple modulation technique, but nevertheless very important modulation technique which has been in use in optical fiber communications from the 1970s till about last 5 or 6 years. And this modulation technique, although I am calling it as simple, is only a relative term because it has its own challenges that needs to be overcome. But this particular modulation technique is simple in the sense that the optical intensity will be directly proportional to whatever the information content that is being used as the modulating signal. And then at the receiver side, you do not have to worry about the incoming signal's phase. If you match the polarization, then all you are looking at is the intensity variations which can be captured by a well designed photodetector, and if possible or if required, most of the times it is required that you also shape the output after the photodetector by a receive filter and then recover the data. So, this is a system schematic diagram of a single channel, single polarization optical communication system that employs intensity modulation and direct detection. So, you can see that we start off with a laser diode here which provides us with a carrier, and if you remember that the way we have written out the carrier is square root PS e power j omega 0 t, where omega 0 is 2 pi f naught is the carrier frequency of the laser diode. For now we will neglect all noises that are associated with the lasers. We will assume that this laser is producing or generating a pure tone at a frequency f naught with a power of PS. Okay, so this is the complex representation, and then we use a Mach-Zehnder interferometric modulator. Now we have talked about Mach-Zehnder interferometric modulator, and we said that if you recall the transfer function in this way, which is given for a Mach-Zehnder modulator. So this is as a function of the applied signal u of t to the Mach-Zehnder modulator. It has it's a periodic function, the output power to the input power ratio if you were to plot on the y axis, and then as a function of the input voltage, you see that when the input voltage is about V pi, the output would have dropped to 0, and then it will be maximum, the output will be maximum when it is 0, when the input voltage is 0 or it is equal to 2 V pi. Okay. If you were to bias this Mach-Zehnder modulator at this point, which is called as the quadrature point, which occurs when u of t is equal to V pi by 2, and then have whatever the signal that you want to transmit as a small signal variation around this bias point, then the output power will be faithful reproduction, reasonably faithful reproduction, which is centered at this particular power. So, this is about half, so it will be centered in a normalized scale to about half, and then any changes that you have applied or any time varying modulation signal that you have applied will be generated at the output. Okay. And this type of a modulation, as we have emphasized many times, is called as amplitude modulation, and it is one of the classes of what is traditionally called as continuous wave or traditionally called as linear modulation or analog modulation technique. Okay. But we are not interested in this analog modulation technique, but what we are interested is in a digital modulation technique. For the digital modulation technique, we need to determine what kind of modulation that we are going to do. For example, if we want to only vary the intensity as a function of the input data sequence, okay, we will assume that the input data sequence or the binary sequence is actually given by a sequence of 0, 1, 1, 1, whatever that is, right. So, it is actually a sequence which consists only of zeros and ones arranged in this one. Of course, these sequences occur every t second, so which means that each modulation period or each data symbol period is about t seconds, and because one symbol is occurring at every t seconds, the symbol rate or the bit rate in this particular case will be equal to 1 by t. Okay. So, this will be usually measured in bits per second. For optical communication systems that employs this modulation technique, the bit rate is typically from 10 Gbps to 40 Gbps, okay, where Gbps stands for gigabits per second. So, it is a reasonably large data rate, but as we will see later on, even this data rate is small compared to the current data rates of a single channel system. that is actually implemented today. Okay. So these symbols occur every t seconds, and what we need to do is to associate two levels of optical power to each of these bits. So for this 0 bit we may associate a maximum optical power, or we may associate a minimum optical power being approximately equal to 0. The ratio of max power in this system to the maximum transmitted power to the minimum transmitted power, which would correspond to either 1 or 0, okay, is called as extinction ratio, and you want this extinction ratio to be as high as possible. Okay. And extinction ratio is usually defined in terms of its dB values, which is given by extinction ratio in dB is given by 10 log of P max to P min. Okay. Ideally the extinction ratio will be infinite because P min will be exactly equal to 0. Now whether you associate P max to 0 or P min to 0 is up to you. Okay. Traditionally we associate P min to 0 and then we associate P max to 1. Okay. So if you want to, so now when you send out this data which is 0 and 1, you want the output power to fluctuate between two values, which is P max and P min. Now how do we go about implementing that system? One way would be to bias the modulator at V pi. So when you have a bit 0, so let us say this is the bit 0 over whatever the duration t seconds that we have. Since the modulator is biased and the input voltage is 0, the output voltage will also be equal to 0, right. So the output voltage will be 0 in this particular case, and it is going to mirror whatever the input data that would be looking like. So this is 0 to 0 mapping. In practice this will not be exactly 0, that is the output power will not be exactly 0. So the extinction ratio is not going to be infinite, but it will be less than some quantity, but still reasonably high, so that we do not really have to worry about this extinction ratio in most of our practical systems. Okay. Now when you want to transmit a bit 1, then what you do is you apply a voltage pulse or u of t pulse with a maximum value of V pi. Okay. So your input is actually switching between V pi to 2 V pi. This is one way of implementing this binary modulation onto this one, and as you can see, when the output voltage amplitude is 2 V pi, not V pi, its output voltage amplitude is 2 V pi, then the output power will also be maximum. So it won't be half, but it would be maximum. Finite extinction ratio means you are going to reduce the amplitude here. So instead of going all the way up to 2 V pi to obtain the maximum, if you were to just go to this height, you apply an amplitude which is lesser than V pi or 2 V pi, then you will be seeing an output which would be lesser. So now the ratio of P max to P min in this case of course is still infinite, because for 0 we are assuming that we actually have 0 output power, but in practice, as I told you, this is slightly above 0, and therefore the extinction ratio is smaller for this blue case compared to the extinction ratio for the red case. Okay. So this is one way of modulating. The disadvantage of this one is that your input u of t must have a DC value which is reasonably high in this case, because when you want to transmit bit 0, u of t should be biased at V pi, and when you want to transmit 1, you want your u of t to be equal to 2 V pi. So what you can do is, you can, instead of working this way, you can pull down this u of t down to 0 and then have a max change of up to V pi. Okay. So how would that go? So this is 0, this is 1, which goes up to V pi and then be back. So the DC content of this waveform is actually smaller compared to the DC content of the previous biasing scheme. But in this biasing scheme, the natural choice would be that a 0 at the voltage u of t will actually produce a 1 at the output, and a 1 at the input would produce a 0 at the output. But if you were to make this logical connection of interchanging what you call as 0 and 1, and you do not worry about how u of t is going to be mapping to that output, and you simply call what we get here as 1 and 0, then it will be all right. I mean, this is after all some connection, abstract connection that we are making at our end. So this is how you can actually generate what is called as on-off keying. Why is it called on-off keying? Because either the laser output is on, which means that it is transmitting some output power, or the transmitter is off, which means it is actually giving out 0 power. So this is exactly what we call as on-off keying, and this is a modulation scheme in which the input data happens to be binary or a bit sequence. Now after modulation, what we do is we actually put this one through the fiber. Depending on the distance between the transmitter and the receiver, your fiber may have multiple spans, span being the length of the fiber before you put in the inline optical amplifier. And I have put this cross to the power n here, as you can see, and this cross to the power n indicates that there are n such repetitions of this span. So this entire thing is one span, and the optical amplifier that we put in here will be the erbium doped fiber amplifier, which we have talked about in the earlier modules. And this erbium doped fiber amplifier will have its gain exactly equal to the loss of the fiber. So the input signal, which is whatever is launched here, will start to decay because of the attenuation in the fiber, and then as it approaches the input optical inline optical amplifier, and after it passes through the inline optical amplifier, the output would be pulled back to its original position. So you can see that it would go back to the original position, and thereafter of course it will again decrease because of the fiber that is kept. Also please remember, the fiber is roughly about 80 to 100 kilometer in one span, and the inline optical amplifier is just about 10 meters. So as far as this span is concerned, the inline amplifier is just one lumped element which has negligible spatial content compared to the amplifier. So now we have propagated these optical pulses. Of course these optical pulses are not going to stay in their time slot. What will happen is, because of the inevitable dispersion, these optical pulses will start to mix each other, or rather broaden and then interact with each other, so that the output would essentially have lot of dispersion. Okay. So and because of dispersion, you will have what is called as inter-symbol interference, and you want to compensate this inter-symbol interference. Now that can be done at the output end, that is at the receiver side, or it can be done by placing strategic amplifiers, strategic fibers called as fibers strategically placed, and these fibers are called as dispersion compensating fibers. The only condition that you normally want to satisfy is that if the forward fiber has a dispersion coefficient of D1 and has a length of L1, then this should be equal to D2 times L2, where D2 is the dispersion coefficient of the dispersion compensating fiber, but its sign will be opposite of D1, and then L2 is the length of the dispersion compensating fiber, L1 is the length of the forward fiber that is used. Okay. So this is how a typical span would look like for most legacy systems. Most legacy systems employ a DCF to compensate dispersion, so that when you receive the optical pulses at the receiver side, there is almost zero ISI. There will still be some ISI because of the last span which is not being compensated, but that is usually too small for us to worry really about that. So you can imagine that this, or you can take it that the input optical pulses that are received at the receiver will be almost ISI free. Okay. Now you have these optical pulses. Of course, what would have happened in addition would be that each of these amplifiers would have given out some amount of noise, that is added some noise to the input, and the signal that you receive will be noisy version of the input signal that has been transmitted. So if the binary data whatever that you have transmitted, the optical pulses that you receive here will be noisy, and further when you convert this optical signal into electrical signal by putting up a photodetector, the output of the photodetector would have an additional noise which comes from couple of sources. One source is the load resistor that we keep, okay, and the load resistor will have its thermal noise, which we have talked about, and there will also be what is called as short noise because of the fluctuations of the source itself and or the fluctuations in the way these semiconductor photodiodes actually work. So you have short noise, you have thermal noise, and then there is also circuit noise which comes by putting up a filter in after the photodetector. Okay. But in this course we will not worry about the circuit noise because that is a subject of entirely of its own, which is very deep subject. We are not going to touch that one, but we will assume that the signal that comes out, the electrical signal that comes out of the photodetector will have additional noise in addition to whatever the noise that the inline optical amplifiers have added. Now there is an important difference that you need to observe here. The optical amplifiers would have added noise in the optical domain, but you won't be looking at the optical domain directly. So you will be looking at the optical domain only with the help of a photodetector. So when you convert that optical or the noise which is signal plus noise in the optical domain back into the electrical domain, you will be seeing that signal plus noise, which is both in the optical domain. So, let me call this as SO and NO, O standing for the optical domain. When you convert this one into the electrical domain by putting up a photodetector, what you are actually seeing is the magnitude square of this. Rather, you would be seeing the magnitude square and the average of this one. So, what you get from the photodetector output, so photodetector output, which would be electrical, would be signal plus noise plus whatever the additional noise that the photodetector would provide, plus the thermal noise that you are going to get because of the resistor that has been employed, the load resistor that has been employed. Okay. All of this must occur in an electrical bandwidth of about BE, which is the bandwidth, the single sided bandwidth of filter that we have kept. Okay. So, this entire noise must be accounted over the bandwidth of B, because that is where the signal of interest is kept and the filter actually cuts off at B. Okay. Now, you look at this S0 plus N0 square, and when you expand this out, you will get S0 square plus N0 square plus S0 N0, right. So, if S0 and N0 are complex, then you will get S0 N0 conjugate plus S0 conjugate N0, right. So, you are going to get these three terms. This is your desired signal, because this is the output photo current is proportional to the power anyway. So, and this is the input power, the optical power, which comes from the desired data or by the actual launch signal. So, this is my desired optical power. Okay. But to this optical power, I have this term which is N0 square, which can be thought of as N0 N0 conjugate, and this is called as noise to noise beating. Okay. The noise spectrum beats with itself to generate this additional noise called as noise to noise beating, and usually this is quite small that we can ignore. The actual statistics of this noise to noise beating depends on the kind of filter, receiver filter that we have employed, and whether we have amplifier before, and if the amplifier is there, what is the characteristic of the amplifier itself. So, it depends on mainly on the inline optical amplifiers, or at least the preamplifier that we are going to place. We haven't talked about it yet, but you can assume, or you can kind of now get an idea that noise itself will beat with itself because of this square law demodulation that we are doing, or rather square law detection that we are doing. Then there are these two additional terms. These additional terms will of course be something like 2 times real part of S0 N naught conjugate, are called as signal and noise beating. Usually, if you place a preamplifier, so this preamplifier would be at the receiver front end, okay, and follow this preamplifier with the photodetector and whatever the receive filter that you have. This preamplifier will be responsible to generate most of this signal noise beating and noise beating, which anyway we can still ignore to the major without affecting the output very much. So, but you cannot ignore this signal to noise beating, okay, and because of this signal to noise beating, you can in fact ignore the short noise and the thermal noise. Okay. So, whenever you employ a preamplifier, you can ignore the short noise and the thermal noise that is given by the, or that is the result of being the short noise in the photodetector and the source, as well as the thermal noise because of the load resistor. You can ignore these two effects because you have a signal to noise beating because of the preamplifier. So, that would be the dominant noise source in all of your preamplifier based direct detection receivers. Okay. So, whether we have a preamplifier or not depends on the kind of application that you have. For most long haul applications, we almost always use a preamplifier, and this preamplifier has a noise which contributes to dominant noise, which is the signal to noise beating. Okay. Now, we will analyze our on off keying system in two cases, one without preamplifier, one with preamplifier, because the noise statistics with preamplifier and without preamplifier are different, they are radically different. So, we will see what these differences are. So, first consider the case of no preamplifier, you have a photodetector out there. So, the short noise and thermal noise are the only noises that come out, and the total photodetector output, I am writing the shorter I here to indicate that this is actually the time varying signal. Okay. So, this time varying photo current will be whatever the input pulse that has been launched. Now, if we assume an infinite extinction ratio, then P0, that is power that is launched when bit is 0 is almost 0, whereas power when you launch a bit 1 will be, which we will denote as P1, will be whatever the maximum value of that you have used. Okay. So, if P0 is approximately 0, P1 can be reasonably large, that is sufficient. So, you need to worry about how small P1 can be above P0, but that consideration has to come from observing whatever the total noise in the system. Okay. We will talk about that. So, we will quantify the performance of these systems by what is called as bit error rate, which is a term that we use to characterize these digital communication systems, which essentially gives you the ratio of bits in error to the total detected bits. Some bits may not be detected, but to the total detected bits, whatever the bits that are there in error, right, will determine the bit error rate. Okay. So, this is in fact not error rate, but rather error ratio, but the term bit error rate is usually used in this sense. So, we do not worry about the bit error ratio or bit error rate, they both essentially mean the same as the traditional usage goes. Okay. So, now you look at the output photocurrent. The output photocurrent would obviously have, we will also make an additional assumption that R is equal to 1, where R is the responsivity of the photodiode. Okay. Otherwise, the input current has to be, or the photocurrent has to be reduced by that amount that we use for R less than 1. Okay. So, to simplify the math, we will use R equal to 1, and the output photocurrent would therefore be of two types, right. So, when you launch a bit 0 or when you send in a bit 0, you have IPH 0. This is my notation to tell you that the bit that I am received is obtained, or the current that you have obtained across, through the photodetector is when I have launched bit 0, and this will be ISH plus ITH. What is ISH variance? ISH is a 0 mean process, or assumed to be 0 mean, and the ISH square, or this is the variance of the short noise, which will actually be given by 2q, the average photodetector IPH, times BE, BE being the electrical bandwidth that we are employing. So, clearly, of course, when the photocurrent IPH itself will be equal to R times P whatever that we have launched. If we have launched bit 0, this would be RP0, which is approximately equal to 0. So, which means that the short noise also can be neglected. So, it is interesting that the short noise does not occur when you launch very low optical powers or when you send out a bit 0. So, you can ignore short noise here, and thermal noise is the current noise whose variance is given by 4 kT by RL over the same bandwidth BE. Okay. And this thermal noise variance will be present, or the thermal noise will be present regardless of what bit you have transmitted. If you have transmitted 0 or you have transmitted 1, it does not matter, the thermal noise will always be present because that is independent of the bit that is transmitted. So, to summarize, IPH0, the photocurrent that is generated when you launch a bit 0, is purely because of the thermal noise. The RMS value of the thermal noise is given by square root of 4 kT by RL times BE. Okay. So, this you need to remember. So, what you will get in the RMS values, if you are looking at, will be the RMS thermal noise. Okay. When you launch bit 1, so IPH1 RMS that you would receive will be both because of the photocurrent that has been launched. So, you have IPH RMS, where IPH RMS corresponds to the signal to, the RMS value of the input signal. So, which is RP1, since R is equal to 1. So, this would be P1, the value of RMS. Okay. So, you can write this as RMS, or you can just write it in terms of the value, peak values. It is all up to you how you would like to proceed, but I am just writing them down to indicate that we are looking at RMS values. Okay. Then to this you need to have short noise, again I am writing the RMS value here, and then you have thermal noise. Okay. Short noise in this case will be non-zero because short noise variance for this case will be 2q P1, the average value of P1 that you have received, times BE. Again, please remember R is equal to 1. So, in all of these calculations that we are considering, R is equal to 1. So, this is what the two photocurrents that you are going to receive when you launch a bit 0 and a bit 1. So, if you observe a sequence of pulses, so you may actually have launched 0, 1. So, let us assume, so we have launched a 0, 1, 1 and 0. Okay, so there are these 4 bits that we have launched, and what is the received current that you would see, that there will be some amount of noise. So notice that the photocurrent is almost 0 when you have launched a bit 0, but then when you go to bit 1, depending, so this height here depends on whatever the power P1 that you have used. So if you have used reasonably large value of P1, then this height will be large, but there will also be increased noise because you have higher value of P1, which means that short noise will also increase. Now on top of short noise you have thermal noise, right. Again here you will still have a short, you have a bit 1 here, because so this is what you had. Okay. Now when you go back to being bit 0, you will have only thermal noise, but this is the case which is actually very good, that is, the system is actually very good, because what you can do is you can put up a threshold here, call this threshold as ITH, I will put a capital I out there, and this threshold is constant, although the line that I have drawn does not really show a constant. And what you now do is to sample this signal at the midpoints of the symbols. So you sample the signals at the midpoints. So this midpoint was actually 2 slots. So this is 1 slot and this is 1 slot. You sample these signals here. Okay. What do you get after sampling? So what you get is, this is the I threshold. Now if you look at the sampled current here, the sample value is actually quite small compared to the threshold value. So you can then assume that the input that has been transmitted, the data that is transmitted, was actually bit 0. Here the sample value is above threshold, next time also the sample value is above threshold, here the sample value is below threshold. Therefore you can put the receive symbols as 0, 1, 1, 0, and in this case you managed to detect every bit, and you detected every bit without any error here. Okay. Now you can make errors in various ways. One, when the noise actually gets too large. So for example, if this is your thermal noise, and then to this if you add a lot of short noise as well, and then you have this lot of thermal noise up there, for 0 you still are not receiving any error. So 0 is all right. 1 instead of 1, because when you now sample here, or maybe the noise level was not exactly like this. So let us say the noise level is like this, the sampled value actually becomes less than 1. So you now revise your bit decision instead of 1 to 0, and here the noise was okay, but it was not so large, large noise. Therefore this bit was still 1, this was 0, 0, 1, and the other last output was also 0. So now you managed to detect all 4 bits, but 1 bit was actually in error, and this error happened because of the noise that was present. Now you can overcome this problem by moving the threshold up. Okay. So you can overcome the problem by moving the threshold up, but that again, what is the optimum value of the threshold depends on the statistics of the noise itself. Okay. We are going to look at couple of expressions and then tell you how the threshold value can be obtained in the next module. Thank you very much.